Hello, welcome back. This is lesson 15 of my playlist, topic 4 and topic 9 of the IB physics syllabus. We're discussing thin film interference. This is HL only content. First, I'm going to show you a demonstration, and I do want you to try this one. All you have to do is to take a glass of water, put some dishwashing liquid in it, and with any loop where I used a keychain, I really want you to observe what I'm about to show you before we move on. Look closely. There. Do you see the colors? And now I can see them in the bottom one. Right, so please make sure you try this before we move on with this lesson. Now pause the video, get up and try it, and come back when you're done. Okay, as a child, you must have played or seen bubbles, and you must have observed that you can see them really nice and colorful. They look pretty sweet. But why do we see those colors? We see them on an oil spill. If you've seen any oil spill on the floor, you might have realized that they look colorful. Why is that? This is the lesson that we're going to discover when thin films show different colors. It obviously has something to do with the wavelength and interference. So let's go. Before we explain how thin films show different points for different colors, we need to remember something from basic reflection lesson. So the one on the left shows how air to glass reflection takes place. Please remember that this reflection acts as a fixed end reflection where it goes through a pi phase change. The part of the pulse that moves on to the next medium continues with a smaller wavelength because it's moving into a heavier medium, but the reflected wave, although it travels at the same speed and wavelength, it is inverted. However, if the opposite is happening, if the wave is traveling from glass to air, for example, where it's moving into a medium where it can move faster, the reflection now acts as a free end reflection where it goes through no phase change. So, now that we remembered this, let's move on to our thin film lesson. Okay, here we see three mediums. First, there's incident ray that is on the very left. The one in the middle is the one that is reflected off the top surface of the thin film that is shown in pink. And the one on the right is reflected off the bottom surface of the film that is shown in pink. The two reflected rays on the right are what interfere in our eyes and form the image. Please observe the phase relationship between the reflected rays and the initial incident ray. The second ray is always out of phase with the incident, and the second reflected is always in phase with the incident. We can explain this by the type of reflection of these two reflected rays. The reflected ray that is from the top surface acts as a fixed end reflection because the index of refraction of the pink medium is larger than the first medium, which is air. However, the reflection on the very right is acting as a free end reflection which goes through no phase change because it's reflecting off a lighter medium compared to the pink one. What does the thickness of the film have to do with any of this? I have adjusted a larger thickness for the medium that is shown in pink. And as shown in this image right now, the two rays that are interfering destructively. Now, the path difference is the first thing we need to understand. The extra path traveled from the first one by the second one is how far it goes in and out by the time it reaches our eyes. So the extra path traveled by the second one is twice the thickness of this film. But the path difference doesn't only depend on the thickness of the film, because the wave is traveling at different speeds in the different mediums. So we have to factor in the index of refraction of the medium that is causing a slowdown, so more delay than only traveling a further distance. When I increase the index of refraction of the third medium, at one point you can see that this wave has switched, because now this third medium has a larger refractive index than the second medium, and it also goes through a fixed end reflection, which means now the two reflected rays are in phase with each other. Let's explain this in more detail. Let's say light is incident through air on a thin film of refractive index 1.6, which is on another medium which has a refractive index of 1.3. If this is the incident ray, the first reflection will take place at the top surface. And since it's reflecting off a more refractive medium, this is going to act as a fixed end reflection, which means that ray will go through a phase difference of pi. The ray will continue into the second medium, and from the bottom surface there will be a second reflection, which will now act as a free end reflection, because the medium it's reflecting off from is a medium with less refractive index. So this is going to act as a free end reflection, which means there will be no phase change, and it will leave the medium in phase with the incident ray. As a result, these two rays are now pi out of phase with each other. One of them reflected from the top surface, the other reflected from the bottom surface of this thin film. And the interference of these rays is what makes the image in our eyes. Remembering from our lesson on two-source interference, if the two sources, the two rays in this case, are in phase with each other, the point on the screen where path difference is 0 would be a constructive interference point, because it's equally distant from the two sources. And that means if there's a crest leaving this point and the crest leaving this point, since they are in phase, traveling the same distance on the screen, they would form a constructive interference when path difference is 0. Likewise, when path difference is 1 lambda, those would be the two distances to that point of path difference 1 lambda. On the diagram we can show that here, where that is 1 lambda. Again, this point would be a constructive interference point, because crest 1 lambda after this point will still be a crest, so the two sources would cause a constructive interference point at that location. Now, if there's a phase difference of pi between the two sources, that means a crest leaving one source is a trough leaving the other source. Lambda distance later, that point will also be a trough. And at path difference 1 lambda on the screen, there will now be a destructive interference point instead of the earlier constructive. If we look at a point where path difference is lambda over 2, these would be the two distances to the two sources, with a phase difference of pi, a crest leaving one source and a trough leaving the other source. At a point where path difference is lambda over 2, that distance is now lambda over 2, which means after the trough, lambda over 2 later, this point is a crest. So this point has now become a constructive interference point. To summarize, the constructive interference point happens at path difference n plus a half lambda, and destructive interference points happen at locations where the path difference is n lambda. Finally, let's discuss how the path difference can be calculated. Now, in this case, the rays are both traveling through air. The path difference between these two can be written in terms of d. When this ray reflects, the red one continues moving in, reflects back off, so it travels a distance of 2d. However, as this red ray travels a distance of 2d, the black ray travels more than a distance of 2d because it's moving faster, because it's moving in a medium which has a smaller index of refraction than this one. We have to factor in the extra distance this travels due to the fact that it is moving faster. So the distance traveled by this first one, by the time the red one reaches the top, is going to be more than 2d. It will actually be 2d times the factor of n, because that's the factor the black ray is moving faster by. So we're going to write the path difference as 2d multiplied by a factor of n being the medium which this red ray is traveling in. So now this is how much further the first ray travels by the time the second ray reaches the top surface, 2dn. And since I'm using n here, we're now going to replace n with m so that we don't get confused. Okay, the last case that we're going to discuss in thin films is the case where the third medium has an index of refraction which is even higher than the middle one. Now, in this case, please realize that the second reflection from the bottom surface will also be a fixed end reflection, which means it will also go through a pi phase change. As it leaves the top surface, now the two rays that interfere in our eyes are in phase with each other as shown on this diagram, because they're both pi out of phase with the original incident ray. So the pattern goes back to the original definition of constructive and destructive interferences, because the two sources, the two rays, are now in phase with each other. The m lambda path difference is now defined as constructive interference, and m plus a half lambda is defined as destructive interference, as it was before in the basic two-source interference that we discussed in topic 4. Again, the path difference is calculated as 2dn as explained earlier. So be very careful about the index of refractions given in any thin film situation. If the third medium is a refractive index of larger value than the second medium, then the two rays are in phase with each other, then the original formulas apply. Only when the third medium has a refractive index less than the second medium, the definitions of constructive and destructive interferences switch, and you use the version given in the data booklet for topic 9 interference part. That's it for this lesson. I will scroll through the screens to show you your homework questions, and my follow-up video will have the solutions of these questions. Thank you.